Hi, this is Joyce Farrell. I want to tell you about recursion. Let's look at a program that does not use recursion so you can understand how methods are called. This short program outputs an A, calls a method named method1, and then outputs a B. Let's assume method 1 outputs a C, calls a method named method2, and outputs a D. And let's just assume method 2 outputs an E. When these instructions are stored in computer memory, each one has a memory address. Computer memory addresses are usually represented with numbers much larger than these, but any numbers will do, so we're just going to number our instructions 1 through 13. When you run a computer program that calls methods, there's a memory location called the stack that holds the addresses of where the logic should return to when each method is complete. Let me show you what I mean. When this program starts, you output an A. Then you call method 1. But before you leave from method 1, you have to remember where to come back to when method 1 is complete. So method 1 is stored at location 3, so we're going to save a 3 in the stack so we can remember where to come back to. Then we're going to execute method 1. We'll output a C and call method 2. But before we leave for method 2, we have to remember to come back here when method 2 is done. So we'll save the 8 in the stack. Then we'll execute method 2, which outputs an E. When you return from method 2, you take the top address in the stack, and it tells you where to go back to. It tells us to go back to the instruction that follows instruction 8. That would be instruction 9, output a D. When you return from method 1, you go into the stack again and get the next place to return to. That would be the instruction that followed instruction 3. That's instruction 4. Output a B. And that's the end of the program. Let's look at a different version of method 1 that instead of calling method 2, calls itself. Method 1 is now a recursive method, a method that calls itself. When you start this program, you output A, and you call method 1, but before you go there, you save the address to return to. Then you execute method 1 and output a C. Then you call method 1 again, but before restarting method 1, you need to save the address to return to. So we're going to save an 8 in the stack. Then you execute method 1, output a C, and call method 1 again, saving the place to return to. You execute method 1, output a C, and call method 1 again, saving the place to return to. Execute method 1, output a C, call method 1 again, and oops, stack overflow. In a real computer program, you might be able to save thousands of instructions of where to return to before you had the stack overflow, but eventually there would just be too much. It's an error. Here's a way to fix it. We're going to create a recursive method called method 3 to have the call to itself depend on an if statement. That way, eventually, when the if statement is false, the method will stop repeating and we won't cause a stack overflow. When this program starts, we'll declare a count and set it to 4. Then we'll output the A, and then we'll call method 3 and send count 4 to it. But before we go, we'll save the location to return to. Then we'll execute method 3, and val will receive a copy of count, so val is worth 4. We'll decide if val is greater than 2. It is. It's 4. So we'll output C and reduce val by 1, making it 3. Then we'll call method 3 using the new parameter, but before we go, we'll save the address to return to. When method 3 executes, val is 3. We'll test to see if it's greater than 2. It is. So we'll output a C, reduce val to 2, and then when we call the method again, we'll save where to come back to and send a 2 in as a parameter. This time, val is not greater than 2. It is 2. So we go to the end if. The next statement outputs a D. And when we reach the return statement, we take the top address out of the stack, and it tells us to return to the instruction that followed number 11. That's the end if, so we output a D, and when we return, we take the next address out of the stack, and it tells us to go to the instruction that followed 11. That's end if, so we output a D, and when we return, we take the next address out of the stack, and that tells us to go to the instruction that followed 4. That's back in the main program, and that outputs a B, and the program ends. So by providing a way out of the recursive method, we've successfully created a method that can run recursively but not infinitely. Thanks for watching.